Yeah, thank you for this introduction. So my name is Nithin, and so in this talk, I would like to talk about our recent work, which uses spline-based separable expansions to do regression and classification, but approximation in general. So what I would like to convey is we would like to discuss our recent submission, what we have done, and what we really do there is we are trying to apply tensor techniques to do modeling of functions of several variables. The focus in the paper is towards regression and classification, so really machine learning oriented applications. However, the lessons we took out of working on this project, we believe it applies to a wider context, and we'd like to partially convey that during this talk. So as many of you may know, the main challenge when you want to approximate functions in higher dimensions is to deal with this curse of dimensionality. In approximation theory, when people refer to this term, they usually talk about a specific term from a specific result by Devore, which loosely states that if you want to approximate a function in d variables within some epsilon accuracy, you will need an exponential amount of parameters to do so. This exponential blowup can be attenuated by the smoothness of the function. So in essence, it says that the more variables you have, the more smoother the function has to be in order to approximate things effectively with an acceptable number of parameters. This comes as very discouraging for people, and it is actually, but it turns out that in many applications, when the functions we're dealing with are nicer, and even though they might be in higher dimensions, they are inherently of low complexity. And with that, I mean that these functions, they have some additional structure, and if you exploit this, you can get around this curse of dimensionality. So one kind of example is, for example, the success in deep networks where they use compositional structures in that context and able to do great work on that. However, in this talk, we would like to focus on another type of structure which also appears, and that is this where the target function f is well representable through a sum of separable terms. So which you see right here. So when you look at this expression, the way to intuitively think about it is that if you treat a function of several variables as the continuous analog of a tensor, then what you see in this expression is really continuous analog of a polyadic decomposition of a tensor in rank 1 terms. So what we're really looking for is like low rank structures in functions. So this topic idea of using low rank, using separable expansions to more effectively approximate functions in higher dimensions, this has been studied by several people already in the past. I would like to particularly mention the work of Molenkamp and Belkin, who have done some considerable nice work on this, and there have been others as well. However, one may wonder why we're revisiting this point at this point. So when we reviewed the literature, we more or less observed that most of the past work focused on using polynomials to approximate the individual component functions. And from our experience, when you're working with polynomials and approximation, you have to be very careful. They can be tricky. There are some properties you need to be careful with. And many of these properties, which I'll speak about later, is that you can get around those by just switching over to spline functions. And spline functions have already been used a lot in the context of computer graphics to model curves. So one of our motivations is to investigate whether using splines in combination with these separable expansions would be a good combination where we can do effective approximation. So given this context of the work, I would like to, the remainder of this talk, I would like to really address the structure as follows. I will first cover some very basic spline basics. And I'll discuss how we exactly exploit low rank structures in higher dimensional splines. Then I'll just outline our regression and classification method, how we're doing it. And then I'll discuss the accompanying algorithm which is used to optimize. So there's some optimization involved, and we explain some things there. And then after that, I will cover some numerical examples in regression and classification. And at the end, I will conclude the talk with some key takeaways and the future work we're getting involved in. So as I mentioned, well, I think I didn't mention it, but splines are piecewise polynomials, and there are several ways to represent them. And one common form is to use the B-spline form. When you do that, you need to first define a set of knots. These knots are the points where the spline pieces are coming together. And it's also the points where the spline loses an order of differentiability at that point. Then after defining the knots, you can, there's a recursive formula to define the individual B-spline terms. Without getting into the technical details, this is the formula right here. But without getting into technical details, I would like to show you how they look like, because there is something interesting about them. So in the case when you take an order 2 spline, an order 2 spline is when you have piecewise linear functions. In that case, the basis terms, they are like these tent-shaped graphs. And one of the key points I want to bring out is that they are compactly supported. So outside a certain knot interval, the function value of the basis terms are 0. And this remains the same as you increase the order. The functions become more smooth. The interval on which the function value is non-zero is bigger, but it's always compactly supported. Yeah, this is a big difference with polynomials, because polynomials they act globally. So given these basis terms, you can use these basis terms to approximate any function by taking linear combinations of these individual basis terms. And you can approximate any contingent arbitrary well by either increasing the knot density, so adding more piecewise polynomial pieces, right? Or increasing the order of the spline, where you raise the degree of the polynomials. And with polynomials, you can only raise the degree, more or less, right? So I will get back about this point later. So now, given a univariate spline, we can now extend it to a tensor product to do splines in in higher dimensions. So here we take, in this expression here, we take a tensor product of the splines. And you can also express that using tensor notation, which we adapt in our group, where this C is the tensor, and when we're taking mode n products with this tensor. But the key point I want to bring out here is that when you're working with this form, the tensor, the number of parameters you have, the size of the coefficient tensor, it grows exponentially with the number of variables you have. Okay, and this is prohibitively expensive, and you can't really do much if you go to higher dimensions. So one of the assumptions we make then is that, what if we assume that this tensor has an additional structure, so that it has this low rank expansion? So what we do then is, wait, why is my, okay, yeah. So what we do then is that we expand, we assume that this tensor has low rank, and we can expand this into a polyadic decomposition. So when we do that, so we're replacing this tensor with its polyadic decomposition. And then once we do that substitution, what we end up getting back is this sum of separable expansions, where each of these component functions are now replaced with a spline function. Okay. And the other thing is that we use the number of parameters, which is first exponential in the dimension to linear in the dimensions, by introducing this constraint. Yeah. So now, given this approximant f hat, yeah, given this approximant f hat, we can do regression and classification by setting up appropriate objective functions and doing optimization over them to train the parameters. So in the case of regression, we used at this point we're just using the standard least squares, right? So we're doing given some samples of a function f, target function f, we take the function value and we subtract the actual value, and then we square it, and then do it sum over all the samples, right? So the quadratic objective function. And in the case of classification, we use this idea where this trick actually where we have this function g which we want to model. So g is this function, this classification function, which maps the unit cube to either 0 or 1, whether depending on which class you belong to. And the way we do it is that we do it with a level set approach, where we have another function f, such that if f is below 0, that point will be belonging to class 0, and if f is above 0, it belongs to the other class, right? So really, we want to approximate f, but we do this through this proxy in this way, yeah? This function 0, 1 is actually, if you notice that, it's a step function, right? So since we want to do optimization over that, it's not nice to work with this discontinuous function. So you replace this, what people typically do is they replace this with a smooth approximation. So they replace the step function with the logistic function. And what you then do is that we get this function g alpha, right? And where we replace the step function with this logistic function, so that we can do optimization, basically. The parameter alpha here controls the transition from one class to the other. So it controls the transition it controls the sharpness of the transition between 0 and 1, right? So from going from a hard transition from 0 to class 1, there's now a smooth transition now. Now, given this, so what we do then is we replace G alpha with, we replace F now with our spline with CPD, polyadic constraints on the coefficient tensor, right? And now we want to train this G alpha now. So the way we do it is ideally speaking, you have a labeled data set, right? And the thing is that the labeled data set, it's either 0 or 1. And ideally, you want your classifier to match all the labels correctly. So in the case where you have all the samples equal to 0, for all the samples for which the class belongs to 0, right? Yi is 0. In that case, you want your classifier to return 0 as well. So in principle, you want to maximize this term you see on the left, right? Simultaneously, you want to also maximize the value of the term you see on the right for all the labels which are equal to 1. And this maximization can be flipped around, and what we then do is you apply a logarithmic transformation, and then we end up getting that this optimization can be reduced to minimizing this specific objective function, where you minimize this log form, yeah? Okay, so now, given these two objective functions, we have to train it with some optimization routine. For that, we use this Gauss-Newton algorithm with double-leg trust region. I don't want to get into the details of how it exactly works, but I would like to mention that this has been already, in our group, we already have worked on this before, and we have developed this method which seems to work very effectively. And one of the key things we do there is that we try to really exploit the multilinear structure in the cost functions to do the training or the optimization efficiently. But one of the key things I want to point out, though, is that in this entire process, the main computational burden in this entire algorithm is to evaluate gradients and gradients. So that's the main burden here. And in the case, one of the things we observed from working on this is that when we work with splines, there's really some benefits there that we can do these gradient and Gramian evaluations very, very quickly. And that has to do with that. If you look at these expressions, these are the expressions we have for the gradient and Gramian. It's not really important to understand what each formula means here, what symbol means. But what I want to point out is that these matrices A, right? These matrices, in the case of the splines, if we use a spline basis, these matrices are typically high structure. They're very sparse, and we can do these evaluations because of the sparsity. We can do sparse matrix vector products very quickly. Yeah, exploring the sparsity. So here you see it. So if you look, this is how the Chebyshev bases look like, right, for the matrix A, and then it's fully dense. And then if you use splines, you would see a very sparse matrix. And this is typically the case when you keep the order of the spline low and increase the number of knots. Choose to increase the number of knots to increase your approximation power. So the original complexity for computing these gradients and Gramians is DIMR. D stands for the number of variables. I stands for the number of function samples you have, so the number of training samples. M is the number of basis terms you use, and R is the number of rank 1 terms you have in your separable expansion. Now, if you keep the order of the spline low and only increase the number of knots, that M term drops away. So this all has to do with the fact that I mentioned earlier that the support of the spline is compact. Yeah, and here we see actually a simulation. So here we're comparing both alternatives using a spline basis or a Chebyshev basis. What we do is we compute here the average time to compute one cycle of Gauss-Newton iterations, and we fix the spline order to 4. We set the number of rank 1 terms to 3, and we have 1,000 samples, right? And we only change the number of basis terms. In the case of the spline, we only increase the number of knots. Yeah, and in the case of the Chebyshev, we raise the degree, and you see that for the splines, as you increase the number of basis terms, you don't really see an increase in computation time, whereas for the Chebyshev basis, you do see an increase. So it's also reflected in practice. Okay, so now let me show some numerical examples. We did some couple of examples, numerical experiments. I would like to show some of them in our talk. The first thing is what we did. We looked at this particular synthetic example where we looked at this function which has 3 separable terms, and intentionally we chose the first term to be a non-smooth term, and the second 2 terms are analytic terms actually. Yeah, but this non-smooth term is to illustrate a specific point. So the first thing I want to show is that here just to show how the algorithm, how the approximant, how this technique behaves, we have a rank 3 separable function. And what we do here is in this simulation, I'm plotting the absolute error using our method where we just take one rank 1 term. In the case when we take just one ranked 1 term, you see that you don't really get any proper approximation. It looks like Rorschach plots right now. It just looks totally chaotic, right? So there's nothing really to observe here. But as we increase it to 2, it's still not great because the original thing has 3 terms. But as soon as I increase to 3, you see that the error becomes very small. So it really shows that after 3, right? If I increase it to 4 now, you don't see really real improvements after that. So it suffices to just use 3 rank 1 terms. Now we did this. We took the same example, the same function, and we did an experiment comparing it with Chebyshev. And what we did was we took either 400 samples or 800 samples of the function randomly, and then uniformly distributed as well. And then what we do is we use our method, and then we plot the root mean squared error as a function of number of basis terms we use. Yeah. And what you see here is that for the splines, you see it continuously dropping. Yeah. But then in the case of Chebyshev, you see that first it's decreasing, but then after a while, it starts to increase. The performance starts to degrade as I increase the number of basis terms. And this happens sooner for 400 samples than for 800 samples. So what's happening here, right? So it all comes back to that non-smooth term we have. So here I'm showing what's happening here is really you're seeing the effects of the Runge phenomenon reappearing. So for with polynomials, there is this phenomenon that when you do interpolation and you have bad interpolation points, you can have this property where you have these large oscillations appearing at the corner of your approximation interval, and these oscillations only become wilder and wilder if you take more and more samples and increase the degree of your polynomial. Yeah, and this all has to do because we're using this quadratic objective function, and that's what you're seeing, those effects coming back why you're seeing that increase, that degradation because of this non-single term, right? So here you see actually a plot where I just take the absolute value function, and then I have 135 uniformly distributed points, and then I keep the degree of the Chebyshev basis to 50, and I take also 50 basis terms for the B-spline. And you see that for the Chebyshev basis, you see these oscillations, crazy oscillations in the corner, but you don't have that for the B-spline because we're keeping the order low and increasing the number of knots. And I would like to point out that this particular oscillations, from a machine learning context, you want to approximate a function from samples, and this function has some underlying smoothness in it, right? And if you're getting these wild oscillations, these are the places where you would have bad generalization error. So you would like to have some better control over that. And one way to do this is to switch over to splines, where you can just control it by keeping the order of the spline though. So the next example is not, what I want to show is not really related to comparing Chebyshev with splines, but it's to apply our method to actual practical problem. So here we have this, we took this NASA data set from the UCI machine learning repository. And this data set tries to model the noise generated by an airflow given some variables. And what we did was we took this data set and we split the data set into a training data set and a test data set. And then we applied our method to see what we get. And this is what we got. So here we see the root mean squared error as a function of the number of rank 1 terms we take. And each curve is a different number of basis terms for the spline. Yeah. And what you see is something really interesting is that after, for the first four terms, you do not really see an improvement in the performance, even if I increase the number of basis terms. But as soon as I go from 4 to 5, you see a sudden drop. Yeah, this sudden drop happens, it seems to, and then after this sudden drop, right, it again stays constant. It doesn't really improve, right? I have not done the simulation further than 7, but I'm expecting it will stay like this. So one of the key takeaways here is that you're now working in 5 dimensions, right? If you had to work with the full tensor where you do not exploit low rank structures, you could have not done things efficiently. And it turns out that you don't really have to, because after 5 terms, there's not much to be gained, it seems. So really with 5 rank 1 terms, you can already do well in approximation. And this kind of reveals low rank structure in an actual practical example. Okay, so how much time do we still have?
We have about 4 minutes.
Okay, so
Please feel free to go into the question time as well if you prefer.
Yeah, I might need 5 extra minutes, so.
Please.
All right. Anyway, so I want to just show an example for classification. So we took another synthetic data set where here's the data set, but this is synthetically generated where we have this, I would like to say this is like Pac-Man splitting an array of energy. You'll see it later, more clear, but we try to apply our method, our classification method on this data set. And what we do is we increase the ranks to see how many rank 1 terms we need to get a good approximation of this classification problem. Yeah. So what we do, we take rank 1, we don't get anything great, right? But if I increase the rank 1 terms, yeah, more and more, as you can see, it starts getting better and better. And eventually at rank 5, you seem to get sort of the shape you expect. Yeah. So this really shows that with this, we can just control with the number of rank 1 terms, we can control, depending on how complex the classification problem is, we can control the number of rank 1 terms, and we can adjust the number of rank 1 terms accordingly to what is needed. Yeah. Now we took the same problem, yeah, and we tried to compare our method with other methods. So we took our the exact same problem, the same classification problem, but what we do is we take different samples. We vary the number of training samples, yeah, and then we plot the number of fraction incorrect in percentages as a function of the training samples, yeah, and we also, on top of that, we also have a randomly generated test data set, and for that we also plot the fraction incorrect, yeah. So we did it for 4 methods. First, our method with 7 rank 1 terms and keeping m equal to 16. Then we took support vector machines with the radial basis kernel, and we took also support vector machines with an order 9 polynomial kernel. And finally, we took a neural network with single layer neural network with 50 nodes, which roughly amounts to the same number of parameters as you have for our method with rank 7 and m equal to 16. And what we see is that in our method, we consistently, for the training error, we can be able to keep it, even for a few samples, we're able to keep the training error equal to 0, whereas other methods are not doing that. And as we increase the number of samples, we see that eventually that our error, after a while, it starts to outperform for this method. Yeah. So we just compare our method with neural networks. We have about the same number of parameters, and we do about the same, slightly better, yeah, in performance. Then the nice thing though is that this is just the result, but there's also this time needed to training. So we have an implementation in MATLAB, and we compared all the other methods were already done also in MATLAB, but with built-in packages which are already available in MATLAB. And what we observed was that we see that our method, even though it's a bit, it's not as efficient for few samples. When you have just few samples, our method takes slightly longer. But as you increase the number of samples, you see that the time we need for training is much less. And also, this is also a regime where our method seems to outperform others. Yeah, so with less computation time, we get slightly better results. So this is just one experiment, of course. Yeah, just with one example, but it does seem to, from these results, we do feel it's encouraging. So we're happy for ourselves that it's working. So yes, that's great. So anyway, this comes to the end of our talk. So let's summarize with some key takeaways. One of the lessons we learned is that using splines together with with these sums of separable terms really seems to be beneficial in several ways. The first thing is that we can really exploit the sparsity in the matrices to accelerate our Gauss-Newton algorithm even further. yeah, by an order of magnitude. And the other thing is it's more, if you're dealing with non-smooth functions, basically non-analytic functions, then there's an easier way to control the Ringer phenomenon by just keeping the order of the spline low and raising the number of knots. Finally, we also showed some examples where you do see low-rank structures coming up in practice. And in the classification method we developed seems to show promise. And so we really would like to extend this work in the future. And the first things we want to do is we want to apply this to other decompositions such as hierarchical Tucker and tensor train. The next thing we want to do is we want to also extend this to multi-class classification. And finally, what I did not mention yet so far is that until so far, we always kept the knots uniform over the interval. This is fine since we mostly used uniform samples over the entire interval, but you can optimize the knots depending on how the function is locally at certain places. And this is something one of our students are actually working on right now. With that, I would like to end the talk and open up for questions.